So gauge fix. So in addition to chiral superfields, there is a construction what is also called vector superfield. And vector superfields are also defined in terms of a condition. Chiral superfields were defined by chiral conditions, that spinorial derivative, covariant derivative acting on them is 0 of d alpha or d bar alpha dot acting. So chiral or anti-chiral. And vector superfields are defined by reality condition. So you have a vector superfield V that is same as V dagger. V dagger is complex conjugate. Dagger I use stars, and dagger sometimes I use interchangeably. So that's what defines a vector superfield. And a vector superfield, now what would be the most general form of vector superfield depends on space-time and the set of anti-commuting coordinates for 2 thetas and 2 theta bars. So we'd have expansion the way we wrote it, expansion C of x independent of theta. And since it has to be real, then C of x has to be real. That is C of x is same as C of x star or dagger. Then linear terms in theta. So theta, which is spinorial object times a spinorial object which chi, which depends on space-time x. So this is shorthand notation of theta alpha up, chi alpha down. And since this is not real and this has to be real, you add to it theta bar, chi bar of x. That would make this real. And there's a normalization we put in here for some convenience. So that is single theta. Then you would have 2 thetas. 2 thetas, I'll use the shorthand notation, this. This is not second component, it's square, right? So a theta square times some m of x. And since it has to be real, then add to it theta bar square m star of x. That would make it real. Then a possible, another theta, 2 theta term could be theta sigma mu theta bar. Again, shorter notation, this is theta alpha up, alpha dot down for sigma, alpha dot up. And this object is real and multiply it by some a mu of x. So this combination on its own is real. This is because A is real. This is real, so this is real. So A mu x is same as A mu x star. Then 3 theta terms. So we can have theta square times theta. Now theta square is theta alpha up, theta alpha down, and this cannot be theta because that will be 3 thetas is 0. So this one has to be theta bar times some object, and we'll give it a name. Yes, lambda of x. And this is a fermionic object, spinorial object. And this is theta bar up, theta bar alpha dot down, lambda bar alpha dot up. And this is not real, so I'll add another term to it, theta bar square, theta times lambda of x. So this and this would be real. I put a bracket here is for some convenience. I would also add an object with a normalization I by root 2 sigma mu bar d mu of chi. Chi is the same chi. You could call this itself a theta lambda bar, but it's convenient to somehow add a piece like this. That's for just convenience. Otherwise, you can write it without that, and then some structure will follow, which will tell you is that we can always add something which is derivative of chi into this. Similarly, for this object, plus I by root 2 sigma mu d mu chi of x. Something is not right. One of them should be, this should be chi bar, right? This is sigma mu bar, which is alpha dot up, alpha, lambda alpha down. This is sigma mu alpha down, alpha dot down, chi bar alpha dot up. That takes care of 3 thetas. Then there can be a term with 4 thetas. 4 theta is theta square, theta bar square, times some object which is d of x. Now this is real. So d has to be real. And again, for some convenience, we'll add with some normalization half of box C of x to this. And C is the first component of the superfield. And there's a normalization 1/2 put here, again for some convenience. Now remember, this object is real. This object is real because of an identity that we had set up earlier for the complex conjugate of a spinnerel chi sigma mu psi bar is same as psi sigma mu chi bar. This identity that we, I think at some stage we proved, that's what makes this object real. Now this object is called vector superfield because there is a vector field in this. Vector field A mu. It has, in addition to a vector field, so many other components. The mass dimension of this vector field, in this definition, we choose to be of V to be 0. And if we choose this to be mass dimension of V to be 0, recall mass dimension of theta and theta bar, both of them was -1/2. That would make mass dimension of C field to be 0 because this is 0, chi to be mass dimension of chi, this is -1/2, chi would be 1/2. So chi and chi bar both would be +1/2. Now theta square is mass dimension minus 1. So m has to be plus 1. And A because this is again minus half, that's minus 1, A has to be mass dimension 1. That's what a gauge field is supposed to be. In order to fix the gauge mass dimension of gauge field to be 1, we have chosen the mass dimensions of everybody else. And then what is left with? Lambda. So mass dimension of lambda or lambda bar, this is minus 3 half, so plus 3 half. And derivative of chi is half, derivative of chi is 3 half. So we added 3 half mass dimension, same mass dimension objects. Mass dimension of D, this is minus 2, so it has to be plus 2. So is the box C, because C is mass dimension 0. So this is the most general real superfield that you can write. Now let me consider chiral superfields I times lambda and anti-chiral superfield minus I times lambda dagger or lambda star. What does that mean? That means d bar dot of lambda is 0, because that's the condition for a chiral superfield. And spinorial supersymmetric invariant derivative of lambda dagger is 0. Earlier when we wrote chiral superfields, they were constructed to be of dimension, mass dimension 1, because we wanted to introduce scalar fields. But this one we'll consider to be of mass dimension 0. So superfield I lambda, which is a left chiral field, we learned how to write expansion for them. The way to write expansion for them was in terms of the shifted coordinate, which was x minus I, x plus I, theta sigma theta bar, and for anti-chiral so there's a sigma mu implicitly here, mu space-time index implicitly on all of them. X mu, y mu, x mu, sigma mu, y mu bar, x mu, sigma mu. So we call the theta independent component to be phi y, and then we have the root of 2 theta psi y, and then theta square fy. And if I expand it, y as this object, then I can write this as phi of x plus root 2 theta of psi of x plus theta square f of x plus I theta sigma mu theta bar of d mu of phi of x plus I by root 2 theta square theta bar sigma bar mu d mu psi of x minus 1/4 theta square theta bar square box phi x. That's simply writing y as x plus this object and make an expansion. This term comes from here as the first, this plus this is the next order from here, derivative of phi times this extra piece, I times that. This is, this object is this plus this extra piece. There's already one theta here, and there'll be two thetas here, and some phase rearrangement has been done here to write it in this particular way. And this is the next order term in the phi. That will be square of these objects, half square of these objects times two derivatives on phi, and half square there is an identity theta sigma mu theta bar theta sigma mu theta bar. I think this identity, did we do it sometime? Somewhere, I don't know if I have it here somewhere, and that is half theta square theta bar square eta mu, something of that kind. So use that identity and then you write it like this, and that is this factor half here, and half will come from second order expansion of phi. So that makes it 1/4, and maybe sine is also coming from somewhere. Where is the sine coming from? Sine is coming from because of two i's in the square. I think this is exactly equal, right? And similarly, you can write now expansion for minus I lambda dagger. Now notice, this object is mass dimension 0. So which means mass dimension of phi is 0. So mass dimension of phi is 0. Mass dimension of psi is plus half, and mass dimension of f is plus 1. Earlier, the chiral superfields that we wrote them with mass dimension 1. So this was mass dimension 1, this was mass dimension 3/2, this was mass f term was mass dimension 2. But here we have chosen this object to have a mass dimension 0, so therefore is 0 plus half and plus 1. Now this is a chiral superfield and this is an anti-chiral superfield. If I add them up, this is not a chiral superfield. Is not a chiral superfield. But it is a vector superfield. Because it's real. It satisfies the reality condition. So what I have done is I have used two chiral superfields, a chiral superfield and an anti-chiral superfield, and I have added them up and constructed a vector superfield. Not a generic vector superfield is not that. Generic superfield is not a sum of chiral and anti-chiral superfield. This generic vector superfield is this. This is a very special vector superfield, which is made up of chiral and anti-chiral.
That's not the most general.
That's not the most general. That is the most general.
So it will have some of these components to be seen.
So it has, in fact, all of these components. You'll see that all these components, but they are, see, unlike here, there are so many independent components, right? Chi, C, chi's, M's, A's, lambdas, and D's. There are so many of them. Wherein here, there are only 3 of them, and they are complex conjugates. Now, in fact, let me write it down. What then explicitly? What this object is? This is phi x plus phi star x plus root 2 theta psi x theta bar psi x bar plus theta square fx plus theta bar square f star x plus I theta sigma mu theta bar, maybe let me write it here, I theta sigma mu theta bar d mu of phi x minus phi x star. This and complex conjugate. Then I have the 3 theta term, I by root 2 theta square theta bar sigma bar mu d mu psi plus theta bar square theta sigma mu d mu psi bar of x. That is a 3 theta term. And the 4 theta term minus 1/4 theta square theta bar square box phi x plus box phi x star. Notice the coefficient of this term. This is the total derivative of phi x minus phi x star. That is, and there is an I in front of it. So it is total derivative of the real part of I, including I. Sorry, the imaginary part of I. So the coefficient of theta sigma mu theta bar is I times d mu phi x minus phi x star. Now, a gauge field A mu changes under gauge transformation as A mu gets shifted by A mu plus I derivative of some real parameter, and I call that parameter phi x I times phi x minus phi star. That's how the gauge transformation acts on gauge fields. If I have to interpret this as a gauge field, then adding to this vector superfield, a vector superfield of this kind constructed from two chiral superfields will act like a gauge transformation on the vector field A mu. Is that clear? The reason for constructing this special vector field I lambda minus lambda dagger was precisely to unravel how would one implement a gauge transformation on superfields, given the fact how gauge transformation acts on vector fields. So this tells us a U1 gauge transformation acts on vector superfield as V changes to V plus I lambda minus lambda dagger. So what we have done, we have generalized the concept of a gauge transformation for vector superfields. And this also tells us why did I choose lambda to be dimensionless? Mass dimension 0 object is because this transformation parameter is supposed to be mass dimension 0. So this gauge transformation, generally we call it theta, d mu of theta, right? Some theta, which is gauge transformation parameter, that is supposed to be mass dimension 0. And that's the reason why we constructed lambdas to be of mass dimension 0. Now, if this is how the gauge transformation acts on vector superfield, then we know what happens to, we can read off what happens to various components of E. For example, what happens to the theta independent component of E, C. C will change from C plus this object. So that C will change, pick up an additional term which is this. What about sides or lambdas there? I want to know chi. How would chi change? So chi will get shifted by this, and chi bar will also get shifted by similarly. Notice that mass dimensions, the way we have assigned them, are consistent with this object because both chi and psi are mass dimension half. Right? Psi is mass dimension half, and chi is somewhere we listed here, mass dimension half. Next is m. And how does m change? Changes by f. and similarly m star. F is mass dimension 1, m is mass dimension 1. And next one is after m, what is the next one? A mu. And A mu we have already seen how it changes. And then is the 3 theta term, lambda. There is yes. Now this combination changes by the amount this. But chi changes by amount psi. So derivative of chi there changes by derivative of psi. So that was the reason to put that additional piece here so that lambda stays invariant. If I had not put that, then the lambda would change by this, but derivative of psi. But this combination, from this combination, if I have to work out how the lambda changes, then lambda does not change at all. Is that clear? The convenience of putting that little extra piece there is at this step. If you don't put that piece, then the lambda will change by an amount which is this object. But lambda, now the way we have said it, lambda plus this object, derivative chi, changes by this amount, but chi changes by chi plus psi. That leaves lambda unchanged, and similarly d is unchanged. And that's the reason to put half box C in this. So what have we seen? You see, what we've seen is that in order to have the gauge field transform like a gauge field, the vector superfield has to transform in this particular way, and the various components of the vector superfield written the way we wrote it there have to transform like this. And particularly, the way we have formulated the vector superfields, lambda and d are unchanged. That's not really surprising. What is the mass dimension of lambda? Yeah. So this could be a genuine physical fermion. And fermion, which is a super partner of gauge field, has to be a Marinow fermion. A Marinow fermion is chargeless fermion. Chargeless fermion does not see gauge transformations. Is that clear? Is that this lambda that we have here, the way we have formulated the superfield, has the properties that it's neutral under SU2 under U1 transformations, and that means it doesn't carry any U1 charge. A super partner of gauge field has to be chargeless because they must have the same charge. For A mu has no charge. But this transformation properties also allows us certain simplification, and that simplification is I can So a simplification. And simplification is that I can make C, chi and m to be 0 by choosing phi plus phi star, which is the real part of phi, to be minus t. Psi to be minus chi. M to be minus f, or f to be minus m. So which means I can choose a gauge condition, which means the lambdas that I constructed in such a way that from the superfield I have here, C, chi and m all 0. And this gauge is, there's a name given to this gauge because the people who introduced it, it's called West-Zumino gauge. And West-Zumino gauge, now vector field x theta theta bar becomes a simple object. Is that it is theta sigma mu theta bar a mu plus theta square theta bar lambda x plus theta square bar theta, something is not right, lambda bar theta bar x plus half theta square theta bar square d of x. Clear?
You're just fixing the gauge here, right?
Yeah, fixing part of the gauge, yes. Part of the gauge in the sense that what did we fix? See, we had so in the general gauge transformation we had so many objects. The real part of phi we have fixed. Imaginary part we have not. And we have fixed psi and f. This object we have not fixed. And this object is what is the gauge transformation. Now for this object gauge transformation is a mu going to a mu. Alpha is the imaginary part of phi. And lambda and d don't change. So lambda is lambda and d is d. D is real and lambda is Majorana. In sense, so which means both lambda and d have no charge. So a general vector superfield with so many components is gauge equivalent under the gauge transformations of superfields to this superfield. Now this superfield has very interesting properties. Now, let me recall mass dimensions of various components here. So let me write here mass dimension. This object is -1, -half, -half. This object is +1. This object is -3/2. So lambda is 3/2. This object is -2. This object is +2. So now if this is a physical gauge field, good enough. It has the right dimensions. This could be super partner fermion with the right mass dimensions. This object is dimension 2. This cannot be a dynamical field. So vector superfield in Weissman gauge is made up of a vector field, a fermion field, Majorana field, and an auxiliary dimension 2 D field. Now this vector field has has some interesting properties. One of them is properties. Let me calculate V square. Take the product of two V's. The only term which does not have a particular theta repeating more than once, because square of every theta component is 0, is square of this object, because this will have at least some theta which is repeating, because if I take square of this object, if I take square of this object, square of this object, if I take cross products of this and this, that will also have too many thetas. So the only term that is non-zero here is this object. Is theta sigma mu theta bar theta sigma nu theta bar a mu a nu. And this object by Fair's rearrangement we have already seen is equal to half theta square theta bar square eta mu nu, that is a mu. Is that clear? That V square has only one term which is square of this. Every other term has too many thetas, and which will make it 0. What about V cube? Zero, because then it will have this times V, so it has already 4 thetas. Multiplying by any of these objects will give me a square of some theta component. So every power of V higher than 3 or higher is 0. Therefore, I can construct an object E exponential of V, and V is dimensionless, so exponential of V is well defined. Exponential of an object should be exponential of a number, dimensionless number. That's well defined. So that is 1/2 1 plus V plus half V square, and no more. And you could put this, all of them together. So what this expansion can be written as 1 plus theta sigma mu theta bar a mu plus theta square theta bar lambda bar x plus theta bar square theta lambda x plus half theta square theta bar square d of x, that is this term plus square of this plus half of a mu x a mu x. So using this vector field, what we have constructed exponential vector field, exponential of a vector field. That's also a vector field because it's real. There's some useful constructions. We'll construct a chiral superfield from this vector field. So useful construction is a chiral superfield, and we'll give it a name W alpha. It's a superfield with a spinorial index, and it's a chiral superfield. What does a chiral superfield mean? W and an anti-chiral superfield. Anti-chiral superfield W bar alpha dot satisfying d alpha bar of W alpha is 0. Yeah, 0 and d alpha of W alpha dot bar is 0. That's what our definition of a chiral superfield is. So chiral superfield and anti-chiral, where W alpha is the following object, is d bar d alpha of B. This is the notation. D bar is d alpha dot down, d bar alpha dot down, d bar alpha dot up. That's a shortened notation for these two d's, d bars. D alpha B. And we'll put a convenient normalization of -1/4. And the corresponding anti-chiral superfield is 1 minus 1/4 d bar alpha dot V. It's straightforward to check that these are chiral superfields. What do we have? The chiral superfield means that this object must satisfy this property. So let's check it. Evaluate d bar alpha on W alpha. That by construction is 0. Because there are 3 d bars. D bars with the same spinel index square is 0. So in these 3Ds, at least 2 of them will have the same spiral index. Is that clear? See, out of this there will be a beta dot here. So beta dot has 2 values, and this has also 2 values. One of them will be common. So you'll have square of d1 dot square or d2 dot square, and that is 0. So this object is by construction 0. Is that clear? Similarly, d alpha, w bar alpha dot, because there are 3 Ds now, unbar these, is identically 0 by construction. So what we have done is that from a vector field, we can construct these convenient chiral superfields. And they have interesting structure that they are made up of 3 spinorial super covariant derivatives of V. Mass dimensions. Remember what was the mass dimension of D? D or D bar alpha dot. Anybody remembers it? Yeah? D, this is spinorial derivative, covariant derivative, even ordinary spinorial derivative, even not even covariant derivative. I made little fuss about it at one stage. Unlike ordinary space-time derivatives, yeah, this is D. One first component is d by d theta. D theta is dimension minus. So d by d theta is so now what is the dimension of these objects? W, mass dimension. Or W bar. But these are chiral superfields. So I can make an expansion for them like I make for chiral superfields. So the theta independent piece, the first piece, would be mass dimension 3/2, because W is mass dimension 3/2. So okay, so that's one property. Maybe second property. The way W's have been constructed, they are gauge invariant. How do I check it? Under gauge transformation, W goes to minus 1/4 d bar d alpha of V plus I lambda dagger. That's how the gauge transformation is. Now lambda and lambda dagger are chiral. This is chiral, this is antichiral. D acting on antichiral is 0 because that's how the antichiral is defined. So that means this term does not contribute here. So what we have is this object is W alpha minus I by 4 D bar D alpha lambda. Now this I can write D bar D alpha as a commutator of D alpha D bar, because D bar acting on lambda is 0 because lambda is chiral. Clear? I can replace this by this. I have not put any index here because the index here is contracted with the index with the first D here. So that's understood. So if I put it there's a beta bar here, there's a beta bar here, a beta dot here, beta dot here. But D bar acting on lambda is 0. So I can always write this as this. But the commutator of D and D bar, I know what it is because I've done that algebra earlier. That's again some sigma times derivative, ordinary space-time derivative, sigma mu times space-time derivative. Remember? So let me write that here. D alpha D bar beta anti-commutator was minus 2I sigma mu alpha beta dot times d mu. This is the algebra we did earlier. So this object I can replace by this. Now look at this, there's a D bar outside here. So let me write this again. It's W alpha minus I by 4 D bar. So this is an object which is this. This D bar commutes with this because D bar commutes with ordinary D mu. So I can take this D bar across this and hit the lambda here, and D bar lambda is, because lambda is a chiral superfield, is 0. Because this object is 0. Clear? So what have we demonstrated? We have demonstrated now that W, the way we constructed it, superfield W, is gauge invariant. Under gauge transformation, it goes to itself. Similarly, you work out this exercise. It's just a repeat of the same argument. There's another interesting property is that W's have. is that if I take a spinorial derivative d alpha of w alpha, that turns out to be the same as the spinorial derivative of d bar alpha dot of w bar alpha dot. The covariant derivative of w and covariant derivative bar of w bar are the same. And this, I think, I'll leave as an exercise. Check this. Apply d alpha. D bar square is d bar d bar. This is square. Is same as d bar alpha dot of d square d alpha d dot d bar alpha dot. This is an identity, and this identity, if you apply there, will tell you this. And if you work this out, this identity turns out bears a simple structure. It's L times d square plus half commutator of d square d bar square. So now we'll use these properties of W to construct gauge invariant, supersymmetric invariant actions. But before we do that, let me write down the vector superfield expansion once again. What I want to do is I want to write down expansion of W in components. But to do that, I have to use the expansion of V and then operate by these derivatives on that V. So let me write down V once again. V of x theta theta bar in the Vesumino gauge was that earlier expression. But remember, y was defined to be x plus I theta sigma bar sigma theta bar, and y bar was defined as x minus I theta sigma theta bar. The expression that I rubbed off, maybe it's in your notes, of V, let me rewrite that as a function of y. So x is y minus I theta sigma theta bar. X is also equivalently y bar plus I theta sigma theta bar theta. So I can write V of x in this particular way. Let me expand this out. This is V of y. Somehow maybe I should write down here what we had written as V of x theta theta bar was theta bar theta sigma mu theta bar a mu of x plus theta square theta bar lambda of x plus theta bar square theta of lambda of x plus half, right? Half theta square theta bar square d of x. Now use this in this in this object. So what do you get? You get the first term, theta sigma mu theta bar of A mu of y plus, in fact, you get y, this component. But I can make further expansion of this object, and then I'll have a term which is square of this times the derivative of v, derivative of this object. Well, let me write out the answer and then I'll justify what the various pieces are. Theta square theta bar lambda bar of y, theta square theta bar square theta lambda y plus half theta square d of y. That is these terms. But instead of y, I would have had this combination here. So I make an expansion there. So I'll get this times derivative of A. This times this by phase rearrangement is again a theta square theta bar square term, and therefore I have a minus I derivative of mu of A mu of y, and this is a derivative with respect to y. Is that clear? Write v of x, write x as a replace x by y minus I theta sigma theta bar, and write for v this kind of an expression where instead of x you have y minus I theta, this object. Make the expansion in the first term, that gives you this plus this. Expansion in other terms gives you higher theta terms. So there are more thetas than theta square and theta bar square. So they will be all 0. So that's one way of doing it. I could have used this in also. That will give me an alternate expression. Y bar y bar y bar and I think there's a plus sign here. I could use either this one or use this one. Now this derivative is derivative, this symbol here y means derivative with respect to y, and this is with respect to y bar. So now I have written v's as a function of y or as a function of y bar, because W bar has to be written in terms of y bars. W has to be, is a chiral superfield, has to be written in terms of y's. So I can use, in order to find out the expansion for this, use the expression of v as a function of y, and here I use v as a function of y bar, and work out these derivatives. Remember, at some stage I had given an expression for the covariant derivatives as a function of y and covariant derivative bar as a function of y. And this object was d alpha plus twice I sigma mu theta alpha d mu y, and this object was simply d bar. We had worked out these at some stage, that the covariant derivative as a function of x, when it was a function of x, it had plus 1 unit this term. When we converted and changed the variables and as a function of y, it picked up 2 here. This object as a function of x had minus this term, but as a function of y, that term cancelled out. It's simply ordinary spinorial derivative. So now d bar, these two d bars are simple because they are ordinary spinorial derivatives. This one is this object. So this, I think I'll leave this as an exercise now. You work this out. Or should I? And work this out and work out that W alpha, which is a function which is of y and theta, because it's a chiral superfield. First component is lambda alpha, this lambda alpha. And it's very easy to see that this derivative, in W there is W, there is square of d bars and one single d. Now look at this expansion here. D bars will kill the 2 theta bars. Single d will kill theta. That will give you alpha, lambda. That's the first term as a function of y. And do a little more of an algebra and then you will discover. Now look at this term. 2 d bars will kill theta bars and 1 d will kill 1 theta. So there will be a theta alpha times dy. There will also be a term d mu a mu for the same reason here. But this term, if you look at it now, when you hit you have 2 d bars this term should go away because then something is not right. Yes, this should have been bar here, yes. See, when this object hits this, so what it gives you a derivative of A, and this has 1 theta, so this will have 3 thetas together, 1 theta and 2 theta bars. Then when you hit by theta d theta bars, those 2 thetas bars will get killed. So you will be left with 1 theta. So you will be left with 1 theta with a derivative of A mu, and then some sigmas, and in fact 2 sigmas. Do a little bit of algebra with that. That will be exactly the term that would come from here, single theta, and will kill this term. Is that clear? This object is the first one that hits V here. So there is a term, this times this, d mu acting on A. So this is new, some different derivative. And there are one theta bar and one theta bar, two theta bars. Then this two d bars acting out will kill the two bars. There will be single theta left. That is the structure of this term, with a derivative of this kind. So that, with a little bit of algebra of sigmas, will be exactly this object, and that will cancel this. So we'll have this, and in addition, there'll be, in fact, there'll be derivative. In fact, there'll be two terms. One, it will be derivative of A mu, and if you do the sigma algebra, there will be one term of this kind, and the other term will be of this kind that I'm writing here. Two sigmas. So you take the symmetric and antisymmetric combination. Symmetric combination will give you d mu A mu, that will cancel this term, and antisymmetric combination will give you this term. I think i's are not there. Okay, that's it. Then there's one more term. This acting on lambda bar. This has two thetas and two theta bars now. These two objects will hit the theta bars and kill theta bars. So you will be left with theta square term. So the next is theta square term. Theta square sigma mu alpha beta dot d mu lambda bar beta dot y. And if you do it carefully, it is minus I. I comes from here. So this is the expansion of the chiral superfield W. Similarly, if you do the chiral superfield, anti-chiral superfield W bar would be written in terms of a y bar and theta bar. This is with respect to y. An interesting thing to notice is that the superfield, chiral superfield W that we have constructed has a leading term which is a spin 3/2, mass dimension spin half, mass dimension 3/2, and the field strength of the gauge field and a derivative. F term is a derivative of lambda. F term was the theta squared term. So we have a super field which has components f mu nu, lambda and derivative of lambda. So this tells you that the field strength, super field that contains the field strength of the gauge field, lambda and field strength are super partners. So these W's that we have constructed here, the V that we constructed here was the super field corresponding to a vector potential, and that was a real super field. And the W's that we have constructed are the super fields corresponding to field strength, and these are chiral super fields. Product of chiral superfield is a chiral superfield. So let me construct the product. Product chiral superfields. W alpha, W alpha. If I construct this, it will have various terms, and since it's a chiral superfield, the highest term is going to be a theta square term. And let me work out what the theta square term is. From the structure that you have, d square y minus 2I lambda of y sigma mu nu d mu y lambda of y, some bars, this one is bar, minus half f mu nu y, f mu nu y, plus I by 2 star f mu nu, f mu nu y, y. The star here is dual. Square of this is theta square d square. That's the first term. That's very simple. Then theta square times this in the cross term. So this times this is the next term. Then square of these terms, that's what a theta, that is theta square with sigma mu nu. So 2 sigma mu nus and theta, 2 thetas. 2 product of 2 sigma mu nus. Do a little algebra that can be written as this and this. Product of 2 sigmas is proportional to an epsilon mu nu plus g's contracted in different ways for sigmas. Means. Is that clear? You've seen that identity? Up to some coefficients. Have you seen this identity before? book. I think I have given it to one of them somewhere. Just use this identity. I think there's a factor of half somewhere here and half here or something. Use this product of two sigmas, and that will give you this term and this term. So there's an I think somewhere here. Maybe this is an I. So use that identity and calculate the square of these objects. And pick up only theta square terms. That's the only one terms I'm writing. Similarly, for the anti-chiral fields, anti-chiral product bar twice I lambda bar y bar sigma mu d mu y bar lambda y bar plus half f mu nu y bar f mu nu y bar minus I by 2 star f mu nu y bar f mu nu y bar. Oh, how much time do I have? Finished. I'll take just 5 minutes. After just 5 minutes, close it. Then I don't have to do it again. Now I think you have already seen what we have is that we have almost constructed the invariant action. We have almost constructed the invariant action. This is a chiral superfield, and this is the theta square term of the chiral superfield. And we have learned earlier, chiral superfield under supersymmetric transformation changes by a total derivative. So in order to write a supersymmetric invariant Lagrangian, I just have to take this object, and that's my answer. So the action, super SUSY invariant action, is d for x Lagrangian density, and Lagrangian density is, I just normalize it 1 by 4 d for x, take w alpha and take the f term, which is the theta square term of this object, and that is as a given in terms of functions of y, and make theta 0 and theta bar 0, that will convert function of y to be function of x, plus Hermitian conjugate. That would be my invariant action.
Theta will be present?
Yeah?
D?
Yes.
It's the auxiliary state, right?
Yes. Let me, and if you write it explicitly, now you just add them up, is that minus I by 2 lambda sigma dot d bar lambda bar minus I by 2 lambda sigma d lambda bar minus 1 by 4 f mu nu plus 1/2 d square. Somewhere I missed the bar. Huh? No, that's I think all right. Oh, this one. Huh? Hmm? And this term cancels between the two. and rest of it adds up. So this is a theory of a Maxwell's gauge field and a chargeless Majorana field, which is supersymmetrically invariant by construction. Oh, that, I think that's taken in. Okay, I think that completes this, but I'll give you an exercise. This is an answer that you have already done. We have an expression of W alpha chiral field somewhere written there, expansion, and we know, use under supersymmetric transformation, how does Y transform? Use these transformations on this Y alpha and show this is show various components of W alpha transform as delta F mu nu is epsilon bar sigma bar mu delta nu lambda minus epsilon sigma mu delta nu lambda bar. This bracket is antisymmetric combination, mu nu antisymmetric combination. And these are the transformations we have worked out earlier when we constructed the vector superfield by iterative construction. And we realized that these supersymmetric transformations, if you remember, we wrote it in terms of A gauge field transformation of A. I'm writing in terms of F here. I can also write in terms of corresponding transformation in terms of A. And we had realized there that the supersymmetric transformation algebra closed on the fields, A field particularly, up to a gauge transformation. Remember? And then we asked the question, can there be a way why does that happen? I think now we understand why that happens. Is because a superfield, vector supermultiplet, which is made up of lambda, A and D, is a Wess-Zumino gauge fixed multiplet, because we have put the C, M and the chi field 0, and therefore we got an algebra which closed only after supersymmetry, up to gauge fields. Supersymmetric algebra closed only up to gauge fields. If we had not chosen that gauge and kept the C, chi's and M's, then supersymmetry algebra will close off shell. is we ask the question, is there a formulation where it closes off shell? If we had done that, we would get, if we had not worked in West-Zumino gauge, we have kept those component fields, then the supersymmetrical algebra will close off shell. Will close without using, sorry, not off shell, without using, in fact off shell also, without using the gauge transformations. Okay, I think I'll stop here and we'll do the non-abelian.